For the first question, we need to find the initial pH of the equation. So at the initial, the HF does not involve in the equation because we does not titrate any of the HF. So the only thing that happen in the beaker is the dissociation of KOH. That makes KOH plus H2O equals, that will give a product of K plus and OH minus and H2O. So to find the pH of this equation, we need to find the concentration of OH because that is the only thing that we got, and use the formula of pH equals to 14 minus POH, and we can get the pH of this equation. So we will need to use the ice table to find the concentration of OH minus. So in this ice table, we will put the concentration of KOH, that is 0.2 molar, and at the initial one. So at the initial, only the reactant have the concentration. So at the product, we will put as 0 and 0, and the H2O will not give anything until at the end. So at the change, we put the X variable because we does not know how much concentration that is being used. So we put at the KOH minus X, and the product will plus X because we will have to use the X. We will get the product as X2 because we will use X of reactant. So we will get the product as plus X. So at the final, we can get the concentration of KOH as 0.2 minus X, which is how much concentration that we use, and the product as X and X. So from this, we will need to find X to find the concentration of OH minus. So we get we are given the Ka of this equation, this question, but we need Kb to solve the equation because it is we got OH minus. So we use the formula of Kb equal to Kw over Ka, and we insert the Kw and Ka. At Kw is 1.0 times 10 power of negative 14, and the Ka that is given is 6.8 times 10 power of negative 4. So we can get the Kb equals to 1.7 times 10 power of negative 11. So we use the formula of Kb equal to product over reactant, and we put the X squared over 0.2 minus X in this equation. So as we know, the X is so small that we can assume that X is very small until it can be neglected. So we write the new equation as Kb equals to X power of 2 divide 0.2. So from that we can find the X. We get the Kb 1.47 times 10 power of negative 11 times 0.2. That is equals to X power of 2. So we can get X as 1.7 times 10 power of negative 6. That is equal to the concentration of OH minus. We get the concentration of OH minus as 1.7 times 10 power of negative 6. So we put it in the equation of POH, and we will get negative log 1.7 times 10 power of negative 6. And the POH we will get as 5.77. But that is our POH. We need to find the pH. So we put it in the equation of pH equals to 14 minus 5.77 and get 18.23 as the pH of the first equation.
So the next question is the addition of 5 ml of HF into 40 ml of KOH in the beaker. So in this question, the volume became additive. So when the volume became additive, we have to work using moles. So first we have to find the mole of HF and KOH by using the formula of N equals to mV over 1000. So the mole of HF is 5 times 0.4 over 1000 equals to 2 power of negative 3 mole. So the mole of KOH is 40 multiplied by 0.2 divided by 1000 equals to 10 to the power of negative 3 mole. By using these moles, we construct an ice table to find the final moles. So by using the neutralization equation, you will get KOH react with HF with the product of KF plus H2O. So when we see these moles, we can see that HF is the limiting reactant. So at the change side, the reactant will minus 2 10 power of negative 3, and at the product side we plus 2 10 power of negative 3. So we get the finals like this. So we can see that KOH is a strong base, so we have to have further reaction, and to have that, so we have to find the concentration of KOH since it is a strong base. By using the formula of mV over 1000, you get the concentration of KOH 1.33 moles. By using the concentration of KOH, we build an ice table. With the reaction of KOH react with H2O, we'll be producing K plus and OH minus plus H2O. So now we want to find the concentration of OH minus. Okay, so we'll fill up the blanks. For the initial of KOH is 0.133 mole and 0 for the products, and we put X at the change because we still don't know how much of it is changed yet. So at the final, we get KOH is 0.133 minus X, and for K plus and OH minus is X. So for KOH is a base, so we have to use KB. So KB constant is the concentration of the products divided by concentration of reactants. So we get X squared minus by S squared divided by 0.133 minus X. Okay, assume that S is negligible, so 0.133 minus S is equivalent to 0.133. So the KB is 1.47 10 power of negative 4 equals to X squared divided by 0.133. So the concentration of OH minus is equals to X, which is 1.4 10 power of negative 6 moles. So by using the formula of POH equals to negative log and the concentration of OH, we get the POH is 5.85, and we get the pH by subtracting 14 with POH, and we get 8.15. Okay, so for question C, it asks us for the midpoint of the titration. So as usual, when the volume became additive, we have to use mole. So N of KOH is 8 times 10 to the power of negative 3. And for midpoint of the titration, it must be M1 V1 equals to 1 over 2 M2 V2. So the half for NKOH is 4 times 10 to the power of negative 3 mole. So like usual, we build an ice table for the use of mole for KOH and HF. So just build it, and for the initial put the mole for KOH is 0.008, HF 0.004, and the product is 0. And the change is, since HF is the limiting reactant, so we minus 0.004 from each reactant, and at the product we plus 0.004, and we get the final like this. So the remaining product in the beaker is the KOH and the KF, and since the KOH is a strong base, so the pH will be determined by the concentration of KOH. So the KOH will dissociate with water, and since it is a complete dissociation, the concentration is the mole is the same for the product and the reactant. So we have the mole of OH minus is 0.04. So we switch the mole into the concentration, and you get the concentration of OH minus is 0.1 mole. And to get the POH, just apply the formula of negative log 0.1, and you'll get 1 as POH. And for the pH, just subtract 14 with 1, and you get the pH as 13.
So for the next question, we need to find the equivalence points of this titration. As we know, at equivalence points, the number of mole is the same. So we use the formula of M1V1 equals to M2V2 as the number of mole is same. So we plug in the M1V1 is the KOH. So we plug in 40 milliliter times 0.2 molar. And V2 we does not know how much is it. So we need to find it, and we put the concentration of HF at 0.4 molar. So we can get the volume of HF is 20 milliliter. So next we need to find the number of moles. The number of moles is the same, so we use the number of moles of KOH, and we plug in the numbers as 40 divided by 1000 times 0.2, and we can get the number of moles is 8 times 10 power of negative 3. So we must find the concentration of KF first. So to find the concentration of KF, we use the normal equation, that is KF concentration equals to number of mole divided by volume, and we get 8 times 10 power of negative 3 divided by 60, which is the total volume in the beaker, divide by 1000 to get liter, and it will be equal to 0.1333 molar. From the KF, we find that F negative is a strong conjugate base that is derived from the weak acid. So the F negative will further react with water to form HF and OH minus. So we drew a ICE table and ICF table to find the concentration of OH minus. So we plug in 0.1133 molar of F negative as the reactant concentrations, and at the product side we put 0 and 0 first because there is no concentration happen. So at the changes we put negative X at the reactant because we does not know how much it is being used, and plus X at both HF and OH minus. Okay, then at the final we can get 0.133 minus X as the F negative concentration, and X at both HF and OH minus. We use the formula of Kb equals to product over reactant. So the Kb is 1.47 times 10 power of negative 11 equals to X to the power of 2 divided by 0.133 minus X. So the X is small, so it is negligible. So we calculate the X and we get X, that is the concentration of OH minus, equals to 1.4 times 10 power of negative 6 molar. So we use the formula of POH equals to negative log concentration of OH minus, and we get POH equals to 5.85. So to find the pH, we just need to subtract 5.85 with 14, and we can get 8.15 as the pH.
So we have to titrate 40 milliliters of HF into 40 milliliters of KOH. So we calculate the mole of KOH and mole of HF, and then use the ICE table and use the ICF table, which is by using the number of mole to get the final number of mole, and then we use the value that we have calculated to calculate the concentration of KF, which is the salt that is produced by dividing the final number of mole by volume, which is 40 divided by 1000 to change it into liters. And then we get the concentration of KF, which is 0.1 mole. So since F minus is a strong conjugate base, it go through salt hydrolysis, which is a reaction with water, and then we have to calculate the concentration by using the ICF table and by using the concentration. So, and then we take the Kb that has been derived from Ka to get the concentration of OH minus. Kb equals to the concentration of products divided by the concentration of reactant, which is also equal to X squared divided by 0.1 minus X. So since the Kb is small, x can be neglected. So it makes it easier for us to count the x squared. So after neglecting the x, you get x is equals to 1.21 times 10 to the power of negative 6 molar. So the concentration of OH minus is x, which is the value of x. And then, okay, so then we calculate the POH, which is the negative log of x. And then we get 5191. And after that, we have to calculate the pH, which is 14 minus POH. And then we'll get 8.09.